JQI today. For those who are looking forward to that, sorry, but there is still the lunch, obviously, after the seminar. So our speaker today is Professor Hong Tang from Yale University. So Hong got did his undergraduate work at the University of Science and Technology in China, and then he came to Caltech for his PhD. I think he got his PhD in 2002, working on nano-electromechanical systems and various topics in condensed matter physics. Then went to Yale to start his own group in 2006, where he's now the Llewellyn-Jones Professor of Electrical Engineering, Applied Physics, and Physics. Hong's group works on a lot of really interesting topics spanning integrated photonics and phononics and superconducting microwave circuits. He's won a lot of awards, including a Packard Fellowship, and he's a fellow of Optica, which is, used to be the Optical Society of America. And I'm very much looking forward to his talk. So, Hong, please.
Thank you. Can I get this here? Hope that people on Zoom can hear me.
Yeah.
Wait. It works. Welcome. Go back. Okay. Well, so it's actually my first time to visit JQI. In the past, I have I'm fortunate to work interact with many fellows over here. Thanks, Kartik, for inviting me. I have a chance to meet everyone in person after 3 years of break. Before I start, I'd like to tell you a little bit about my research interests. So the overall theme of my research is to build a hybrid photonic chips to manipulate the photon on chip and study enhanced light matter light structure interactions. So we study optomechanics, the light interaction mechanics, and the light interaction with spins, and the integrated nonlinear material to study light-light interactions. Today, I will focus on the third topics, integrated nonlinear optics, and with special focus on the integrated quantum frequency conversion. So the motivation of building chips scale integrated devices or chip scale integrated quantum optics is scaling. So here is a boson machine that was developed by the USTC by Jianwei Pan's group. And you can see here there are a lot of detectors and beam splitters. So it is an expensive system, even though it's both as a tabletop system. The actual support infrastructure way bigger than the tabletop. So if we can integrate all the detectors, beam splitters, and the sources all on the same chip, you would have a true scaling advantage. So that is one motivation. Another motivation is quantum networks. So a lot of us envision that the future quantum network will consist of sort of a quantum computing node that are connected by transducers, which distribute entanglement between different nodes. So these are picture that was announced in 2020 by ETH Zurich group. So they demonstrated the first quantum link between two superconducting systems, and they used physical cryogenics link to connect this system. Most of us believe this can be better done with a fiber, where you could distribute your quantum information over a much longer distance. So those transducers are very difficult to build, as you can imagine that the superconducting system, they operate on microwave photons. When they come up to the room temperature, you will lose your quantum coherence. So this can be done with integrated chips where you have enhanced coupling between night and the night. So in terms of integrated photonics, we know that the silicon photonics is quite advanced and they're very commercialized. One main drawback for silicon photonics that it does not have the desired nonlinearity we like to have to achieve frequency conversion and to build a quantum optics system. So most quantum optics utilize Chi2 nonlinearity, and silicon is a symmetric crystal. So that does not allow you to give you like second harmonic generation, frequency mixing, frequency down conversion, those kind of function. So in my group, we spend a lot of effort trying to integrate different type of nonlinear material in the photonic platform. Our specific focus are really Chi2 material. Also, of course, the integration also include that you also like to detect a photon with a very high efficiency. And for microwave-to-optical conversion, you also need the superconductors. So for photon detection and for supporting microwave photon, we also integrate superconductor on part of our chips. So there's a hybrid integration, basically nonlinear material and superconductors. So, so in the context of manipulating photon on a chip, I'd like to organize my talk today in this following way. First, I tell you how we detect photon in the most efficient way, and how we generate the photon pairs on the chip. And then I'll close by talking about frequency conversion. So, so those this boson sampling machine, they have a lot of detector here, and these involve like 20 input mode, 60 output mode. So those detectors are superconducting nanowire detectors. A lot of you are very familiar with this detector. It's basically a long meander, and that you shine light through a fiber to this device, and when a photon land on those nanowire, superconducting nanowire, normally made of kind of an albumin nitride or titanium nitride, or some higher TC superconductors. So it's generally a hotspot, and you put a current bias on those wires, and under this current bias, your hotspot are going to expand and cut off the current. So when you cut off the supercurrent, you can register that supercurrent and give you a click, and you can detect single photons. So these detectors are very powerful. A lot of you are using it. The one drawback that it's not very scalable. So back almost like 10 years ago or 12 years ago, we developed a different type of detectors that integrate this nanowire on a waveguide here. And because of the enhanced coupling between the negative supporting a waveguide and the superconductor, you can achieve a very high detection efficiency. And the nanowire also much shorter, so that gives you a high speed. So most importantly, this kind of geometry allow you to print a lot of detector on the same chip. So you can scale up the number of detectors. So that allow you to make many detector on the same chip to analyze your photonic state. One problem with this detector is that the on-off switch, they cannot resolve a number of photons in each of these pulses. They can detect the presence or absence of photon, to achieve ultimate analysis of a photonic mode, you need to have a photon number resolving. So one problem we tried to solve a long time, can we resolve a photon number with these kind of detectors, with this nanowire detectors? We had an idea, but it took us quite a while to work it out, almost 5 years to get it working. So here's these, it's called a photon number resolve detector. So if you're familiar with the photon number resolve detector, there's a commercial solution. For example, there's a transition edge detectors. Basically, it's bolometers that work at a millikelvin. and you can detect up to 10 photons with very high efficiency. The drawback is the speed is relatively slow because the bolometer under temperature and thermal conductivity goes down, and this response speed normally at 10 microseconds. So our nanowire detector target to solve this problem by providing large number of photon detection and also achieve high speed. So here's how this detector works. Looks pretty complicated. I'll walk you through. At the middle is a waveguide here made of silicon nitride. And we expanded the waveguide, adiabatic expand to wider. So when we make it wider, and now we can pattern a lot of nanowire over here, okay, individual nanowires. And those nanowires are connected through those blue trace, which is a transmission line made up of niobium nitride. The nanowire is also niobium nitride, so same material. And the light velocity in this transmission line is reduced by a factor of 100 compared to the velocity of light in the waveguide. And so then you, when the photon land on one of the detector, it's sent to alpha pulse in opposite directions. And those alpha pulse propagate to this impedance transformer, go to 50 ohm. So you register 2 pulses, measure the time difference, arrival difference, and you can infer which detector flash. So you see also those yellow trace. These are bypass circuits. Also make on-chip superconducting inductors and on-chip resistors. Really need to reset this detector after flash. So each of the detector can detect a photon independently. We have 100 detectors over here with almost like 200 inductors, plus these 2 impedance transformers. That's why it looks very big. This device is pretty complicated. It actually works. So here, what do you see? Oh, by the way, so these, all right, let me go back. So this alpha pulse can traverse the whole circuit within only 100 nanoseconds. So that means this count rate can go up to 10 megahertz. It's about 100 times faster than the bolometers. So each of the detector, the time travel from neighboring detector is 1 nanosecond. So you basically have about 100 bin in those detectors. So these are typical oscilloscope trace you observe when you send a photon pulse into the device. And so here we send a thermostat with average photon about 6 photons per pulse. And you can see that for the first pulse, you register about 16 photons here. And for the second pulse, you register 2 photons. And you repeat this 1,000 times, you build this histogram here. And you can see that these photon statistics follow the Bose-Einstein distribution very nicely. So this works extremely well. And now if you send a coherent state in with the same number of average photons, 6 photons, you can see that you see a Poissonian distribution. Okay, so very clear difference. Yes.
Yeah. So on the top trace, what does it mean that the pulse height seems to be getting smaller toward the end, the second half?
Yeah, very good. Yes, it gets smaller. So the red dash is a threshold, right? So when above threshold, we register there's a photon click. So to get smaller, the reason is the following. And let me go back one slide. So when the photon microwave pulse propagate along this direction, other direction, these like meters and meters of long of delay line, they do have a propagation loss, the microwave propagation loss. The reason it has a loss because we add a layer of a high K material on top of a superconductor to slow down the microwave. Then that high K material adds some microwave loss.
One other, you mentioned 100 nanosecond
Mhm.
to traverse it.
Yeah.
If they come faster than that, is it possible to still deconvolve the click so you can actually go beyond that?
Yeah, you can. So it's really determined by your detection electronics. So if you can see that each beam is 1 nanosecond here. So if we design this research cycle fast enough, and also if I have more expensive electronics, you can do faster. Yeah. So the loss is not really significant. After 100 detector, you lost by about 3 to 4 dB. It's still way above the threshold. So it didn't impact our measurement. Yeah. So it'd be just a transmission and loss. Thank you.
Should I think of these peaks as single photon detection?
They are.
So then if I have 2 detectors on each side,
Mm-hmm.
then either the photon is absorbed to the top or the bottom.
Mm-hmm. Statistically, probabilistically, yes.
So why do you have 2?
I have 100, not just more than 2.
No. Why do you have one at top, one at the bottom?
Oh, just to reduce. Okay. Very good question. So these design principles are quite simple, right? It takes us 3 years to develop process of fabricate because it involves 7 layers of E-beam lithography. And it's really important to reduce the footprint of a device. So we don't have a dirt land on this area, like a rain 1 centimeter by 1 millimeter area. And that's pure university clean room does not have good control of contamination. And we want to fold the device. So we want to reduce the footprint.
Second question is about related to Alan's question. If these are single photon detection, then why the strength of this peak goes down as we go further in time? Is
Yeah.
Loss after the detection in the wire, or because the loss before the detection doesn't matter?
Right. So it is you see these are there are a lot of inductor here. So there is inductor. Each of the detector have 1 inductor here. So this blue trace is a very long inductor. So for the microwave pulse to propagate to all the 100 nanosecond path, there's dB per meter loss still coming to hurt you. Okay, so to see these average photon numbers still 6, and you can clearly see the different statistics of thermal photon and coherent light. And now if you increase the number of photon in each pulse, you can see that now you can detect a lot of photon, but it's a little bit deviate from the Photonic distribution. The reason we have more photon here, there's a chance 2 photon hit 1 pixel, and now your model becomes not valid anymore. You need to correct your model. But clearly, you do have that capability to detect a lot of photons. So we are really excited about this result, and there are a lot of more things you can do. For example, you can use this detector to do very high order correlation measurement with your impulse input mode. You can normally do G2 measurement. We do every time, all the time. But with this detector, we can do up to G15's correlation. So you really can diagnose that photon mode very nicely to very deep level. And you can.
Can you please say anything about crosstalk in the system? Is there any crosstalk that has 100 detectors? Would the detection of one photon affect a full detection of the photon of a different detector? And then if you have a field factor of about 50% in the slide.
Yeah, so one way to address crosstalk is this yellow trace. And that has a little resistor here made of a titanium. Those are basically those white bar here. We designed to be around, I think 100 ohm. And here this inductor. So when these detector flash, these become normal, okay? So the supercurrent has to be routed this way. So it continues. And that's really address quite a lot of crosstalk problem.
What is the operation temperature of this device?
These are the 1.6 Kelvin. It really, you can do anything below 2.5 Kelvin will be fine.
Yeah, you mentioned the titanium was resistive, so I was wondering. Yeah.
It's a normal state resistor. Yeah.
Yeah.
And we don't want to go below 500 millikelvin. The titanium becomes superconductor.
Yeah.
See those Einstein statistics, don't you have to have a bandwidth for your thermal light, which is smaller than the detection time window? Like,
Yes. A lot of detail over there, and that's you can find. There's like a 20-page of supplementary material talk about how to prepare those thermalized state with our different switches. Yes. You're interested, you can look into this archive paper. You have a lot of filters to control the pulse. Yes, go ahead.
In these plots, like the one with all the dots on there, you only have. I noticed that there's all these like colored dots that are neither pixel is not fired or pixel is fired. So what do those represent?
Oh, okay. So each of this row is one snapshot, one trace on your oscilloscope. Okay, my laser disappeared. Here, come back. So each one trace is one snapshot of one trace on the oscilloscope. This will correspond to one pulse. Okay. The next row is the next pulse here, and so the different row I represent by different color. So when it flash, one of the detector flash, and it's a solid color, and it's not flash. It's just that time being is empty. You don't see any pulse.
Okay, so I guess I'm still a little confused here about this. So you're saying that the differently colored dots in that like plot there are just
different pulse coming in the time domain. Pulse coming in, pulse coming.
So the like darker colored ones are all just the same pulse within the same measurements.
Right. So imagine there is a one here. Maybe I should go back again. So suppose where you got one pulse here. In this pulse here, there are 3 photons in that pulse. Okay, and the 3 out of that 100 detector flash. So you have will be 3 solid dots.
Okay, but what I'm trying to understand is the like different colors of the dots that you're showing in the plot there.
Different colors. So for example, I assigned this the red color, this one the blue color, and it's just I can use the same color. I don't need to.
So I guess that's all
just a cosmetic.
one pulse from another. So
Yeah.
if they came from the first, so I guess you're able to somehow tell which pulse each of these came from. Or okay, so that's just the different pulses.
Right, but remember the waveguide is short. It takes very short time for the photon to traverse. Much shorter than coherence length of that photon. Okay, so there are actually you can in the remote sensing community, people are very interested to tell the difference between thermal light and a coherent light. So this detector can reach quantum limit of that discrimination. You can also do photon subtraction. And that's kind of a trick you can play with any photonic state. So just give an example of photon subtraction. So if you send the thermal light state into your detector and you don't subtract any photons, you have this Bose-Einstein distribution. Now, if you pick one of the detectors, for example, the first detector, condition on the flashing of that detector, or you can subtract 1, you can pick 2, and you can subtract 2. So as you subtract the number of photons from your input mode, you can see start transition from thermal distribution to more like a Poissonian distribution. And also the average photon number increase. And that's just to reflect the bunching nature of photons. And you subtract a photon, your average photon number increase. So there are a lot of interesting things you can do, and you're welcome again to look at that paper that we play a lot of trick with those detectors. All right, so I hope we'll convince you that it's good hybridization, right? For this superconductor on your waveguide, you can really achieve quantum limited detection of photons. So we also work a lot of long time work on photon generation on the chip. So for that, we need a nonlinear material. So here I'm showing materials, a photonic material with a Chi2 and a Chi3 nonlinearity. And this triangle means material with a Chi3 nonlinearity. Most of this material are silicon photonic material, like alpha silicon, crystalline silicon, and high-deck silicon nitride diamond, silicon carbide, cubic fixed silicon carbide, tricargillide. And here's the band gap, and here's Chi3 nonlinearity. A range of material has Chi2 nonlinearity. For example, 3 arsenide, gallium arsenide, aluminum arsenide, gallium phosphide, nitride, lithium niobate here, and aluminum nitride. So you can see the Chi2 here, we color coded here, Chi3 on this side, they both invert somehow depending on the band gap here, right? So if you want a large nonlinearity, choose a narrowband semiconductor. Of course, that will be cross problem. You have a multi-photon absorption, and a lot of cases you really want to avoid 2 photon absorption, 3 photon absorption, or this higher order photon absorption. So it's no wonder that the aluminum nitride is a material that we really our preferred material because of very large band gap here. And so in the following, I'm going to just show you aluminum nitride device we made for photon generation for frequency conversion. And you can do the same thing with the lithium niobate. So all the devices I made with aluminum nitride, you can do the same thing with lithium nitride, gallium nitride. So aluminum nitride. So the material is quite scalable. You can deposit this material with MOCVD and large wafers and bunch of wafers. And because of the MEMS industry and solid state lighting and the power electronic industry, and those material right now, the device processing are very industrialized. So those we leverage to create our devices. So the material, the 2 type material we've been using, one is a polycrystalline aluminum nitride, which is sputtered on the dielectric layer to create a waveguide. And those are polycrystalline, but the domain is very small, less than 20 nanometer domains. And that's why you can have a high Q. And if you do X-ray rocking curve, you see about like a 2-degree rocking curve anyways. And the roughness on the surface is about, as grown material is about 3 nanometer. You can polish it down to like above 0.1 nanometer roughness. And the other type material is a single crystalline aluminum nitride that done by MOCVD grow on sapphire here. And you can see that the X-ray very narrow 9 ways, and there's no domain, and the roughness is much smaller. The typical your silicon roughness, you can punish even further to go down more smoother surface. And with this material, you can get a pretty high Q, and in the telecom, you can get more than 5 million. And down to UV, we can get about 300K Q. So it's very broadband thanks to its large band gap. So to have efficient light conversion on a chip, you need to satisfy the phase matching. And these quite convenient with particular those aluminum nitride waveguide that you can do this geometrical phase matching. So you can vary the width of this waveguide. And as you vary the waves and the refract index of your fundamental mode and the harmonic mode can meet at a point at the width like 1.1 micron here, now you get a phase matching. So you can support all different modes that have the same phase velocity, and then you can get a phase matching. So once you get a phase matching, you can test that phase matching by doing second harmonic generation. You can send, for example, fundamental 1550 nanometer light, and you can look at the chip, and when it glows, you know you got a phase matching. So the second harmonic efficiency we normally represent by percent per watt because it's a is second order and optical nonlinearity. And so with the polycrystalline nitride, we can get a 2,500% per watt of a conversion efficiency. With the silicon, with like single crystal material, we can get a 17,000% per watt kind of efficiency. So we kind of obsessed with the number. The reason that the higher the number, the higher the conversion efficiency you can achieve. So here's a typical kind of a light-night curve. You plot is a pump light, and this is second harmonic generation. So when you have in a low power regime, you have a really quadratic dependence of second harmonics as a fundamental mode. But when your power becomes large enough, you can see that you deviate from these quadratic dependence. The deviation happens because your fundamental mode of light coupled so strongly with the second harmonic. The fundamental mode of 1F, 2F start to hybridize. And you have a form a new set of a super mode. So that super mode, you can measure that super mode, look at the transmission through the device under a strong pump condition. So you can see that the splitting of the mode. This only happens when you have a phase matching direction. So if you go backward, there's not a phase matching, you see regular like a transmission dip. So you can see that contrast look like an electromagnetic induced transparency. It's just really very strong coupling between micro-to-optical mode. And a lot of people develop like optical isolator based on this similar principle. So with that mode splitting, you can actually estimate what's your single photon coupling rate with this 1F 2F coupling. And there are a lot of new things you can study over here, including frequency conversion. So what is the application we have explored with this very strong second harmonic generators? And so with this device, you can create a new color of light. Clearly, so sometimes you need to address like atomic clock, you need 780 nanometer, you need very narrow line width. And the way we can do it, we can get a cheap telecom lasers, frequency stabilize it, and double it. And we have shown that we can double to like 778 nanometer to address the two photon transition of rubidium 85 and also rubidium 87, really for metrology applications. One of the challenges to address this specific transitions, you need to tune your resonator to exact wavelengths. Because those are resonant Dopplers, the phase matching window is pretty narrow. So you have to combine the device multiplexing. We have a device that have 16 resonators on one single pair of waveguide. So you have 16 resonant within a free spectral range. Here, the example I'm showing you have 8 resonator on the pair of waveguides. You have 8 resonance. So you can see that you can control each resonance very precisely. And each of these rings only vary the dimension by about 10 nanometer, either radius or the width. And you can hit the atomic transition. So that's the idea to use for integrate with some of the clocks. So you can also do this down conversion, build OPO. Kartik has a lot of work on that too. And so the idea is that you split the photon, use the same second harmonic generator. You instead of a pump out 1550, you can pump out 775. Then you can build OPO over here. The threshold is really low over here, couple of milliwatts, and you can produce OPO over like 120 nanometer wavelength spacing here. So you can build a laser with this kind of OPO system. With lithium niobate, this threshold can be even pushed much smaller to microwatts because of much higher optical nonlinearity. So this optical nonlinearity really determined by this fundamental harmonic coupling. So in our case, our 17,000% per watt corresponds single photon coupling rate about 80 kilohertz. So that's OPO. So if you drive the OPO just at a threshold, and so you would have a squeezer, and measurement of squeezer is much harder. So actually, the way we try to quantize this OPO at a very low pump powers to measure photon pairs. So you can drive even below the threshold of OPO, far below the this squeezing pump required. Pump for squeezing, you can generate photon pairs. You can use a pair of detector I showed you earlier to analyze the photon you generated, and you can. This experiment shows that you can produce very bright photon pair source with those kind of a second harmonic generator or OPO devices. Okay, so those are photon pair generation or photon conversion on the chip. So any questions if I move on, talk about frequency conversion? Yes.
How do you distinguish the spontaneous parametric down conversion through a filter, which is the ring, from the oscillation? Is there a power dependence if you can clearly see that? How do you know when the threshold is?
How do I know the threshold there? So when you want to generate a pair, there's no threshold. You go as low as you can. You measure the signal to noise ratio, and you make sure you have the brightest source available for you. Yeah. So really, you just at that time we didn't know. We didn't even reach the threshold, and only about a couple of years ago we started to reach the threshold.
So it's only when you can see a macroscopic signal on spectrum output.
Exactly. Yeah. Exactly. Yes.
So we're saying that the white matter for parametric down conversion, right? And also for SAG.
Can you repeat your question? Sorry.
Well, you said that the peaks are quite narrow, particularly for SAG.
Yeah, the peak is quite narrow. Yes.
And isn't that what you want for the atomic system? Because one would think that the narrower is the peak, the better you can basically not just match the position of the resonance, right? But you also could have exactly the same or similar shape.
Right. It's not as narrow, but so what happened that if a second harmonic generator, right? Your second harmonic of 9 ways basically determined by your pump 9 ways. Same thing as OPO. So you're not doing better than where the source laser is. But in atomic transition, you want better than that, right? So you need to stabilize your source.
Start with the female laser, about the quite thin lasers, 50.
Yeah, that's what set your 9 ways. Right, the bandwidth of the doubling bandwidth is larger than your laser 9 ways. It's much larger than your 9 ways. It's always like hundreds of megahertz or gigahertz, tens of gigahertz.
Even in those.
Even for the resonant Doppler, yes, because those are small chips. Yeah, it's not like your free space Doppler, the very critical. And here we have a much larger bandwidth. The bandwidth of those Dopplers like 1 or 2 gigahertz without the tuning, without heaters, without using thermal tuning. If you use thermal tuning, you can increase the bandwidth by a larger factor of 100. Right. Okay, frequency conversion. A lot of you familiar with that. I'm not repeat that. So the challenge is really try to build a bridge between different type of a quantum system. As you can imagine that there are a lot of different quantum systems being built, and you need a frequency conversion from one color of like 780 nanometer photon to 1550, like what I mentioned earlier. And you also need to build a frequency converter, for example, from superconducting qubits to like a Telecom system. So what is the actually quantum frequency conversion? So we regard the quantum frequency converter as similar as classical radios, and you basically have all the information encoded on a carrier, and you convert it to another carrier. This could be 10 gigahertz, that would be 200 terahertz. So the requirement that when you only change the carrier frequency and you don't change the statistic of the photon properties. In other words, if you plot in the IQ space, you want to look at your after demodulation from a new carrier, the IQ looks the exact same, or the Wigner function looks the same. So that put a very stringent requirement on those frequency converter to really distributed entanglement between a different system that you ideally would like a unitary conversion efficiency. There's no loss, zero loss. Of course, you don't want to gain, because any gain will also introduce just change your photon statistics. And you do not want to add a noise to the system. You want a reasonable bandwidth. So those are parameters we drive in our devices. The physics involved a lot of our work involve nonlinear optics. Same as our second harmonic generator I showed you earlier. And here, most of the case, we configure in the three-way mixing configuration. So if you write down these Hamiltonian, you quantize the electric field, and a very simple three mixing Hamiltonian. Of course, you can use a four mixing, that will be four operators. So in most of the case, we drive one of this mode very strongly. I use a stiff pump, that's your local oscillator, and you reduce one of the operator to a number here. That's the photon in your pump mode, and that's your single photon coupling rate. In our case, our single photon coupling rate basically is this integral that involves the mode overlap of a Chi2 material with all your three coupling mode, and here the mode volume. So you see the clear advantage of making on-chip devices that the small mode volume help here, and that really can enhance your coupling between different color of light. And so once you do the stiff pumping operation and your three mixing Hamiltonian reduced to a kind of a beam splitter Hamiltonian, you have excitation exchange between B and C mode if your A mode is a pump. And the figure of merit is often described by this called cooperativity, which is really the exchange rate between the B and the C mode divided by their loss. And that eventually determined by the quantity factor of these two coupling mode and the mode volume. Again, it's Q over V, Q over V. So you really want to make a smaller device to improve your Q over V, like Purcell factors. And often we want this cooperativity to be one to have a unitary microwave to optical conversion or optical to optical conversion. But in real device implementation, you have other factors because we're using cavity, and the cavity and the noding condition also come into play here. There's a prefactors. So if you have fully overcoupled system, like superconducting resonator, you often fully overcoupled by factor of 100. So this number is almost 1. But optical domain, that's always a compromise. So you normally don't have a high overcoupling ratio. So those are the requirement. You have a high Chi2 nonlinearity, high Q, small mode volume, phase matching, all those what you engineer for high second harmonic generation efficiency. Same thing you would require to have efficient frequency conversions. So a lot of us in the community, we try to generalize these nonlinear conversion process because the conversion process over here, this ABC mode, we often treat as optical photons. And they could be microwave photon, or mechanical resonance mode, or spin Magellan mode. And the physics is exact same cooperativity you need to optimize. And the Hamiltonian is actually the same. So if you look at like Chi2 nonlinearity, that will be the E field coupled together of a coupling mode. If you talk about Park-Hell's effect, the one of the E field is microwave mode. Okay, so that is basically what we utilize for this Park-Hell's cavity electro-optics, microwave to optical conversion. We utilize this term here, Chi2 nonlinearity. And you can also write the component, the magnetic interaction term. You also have a similar Chi2. Those are relatively weak. And you can replace one of the E field with the H field. And this is the Faraday effect, okay? So this is where the spin involved, a Magellan involved, a Magellan mediate microwave to optical conversion or things like that. So this new is a Verdet parameter, and those about 2 order magnitude weaker than the Pockels effect. And that reflects your G0, single photon coupling rate is about 2 order magnitude smaller, 2 or 3 order magnitude smaller. So if a system have a strain, then you can write a new type of remixing term that involves the strain. Now your coupling efficiency also actually increase compared to the spin coupled system, and become a comparable or even bigger than the Chi2 nonlinearity. And here basically the cavity optical mechanics is based on. Of course, you have an even other order of a term. There's a magnetic restriction that also can give you frequency mixing. Those are much weaker effect. So in most of the system that we utilize for microwave to optical conversion, even optical to optical conversion, we normally use the electro-optical Pockels effect or Chi2 effect or the cavity optical mechanic, because the single photon coupling rate is always bigger. So here's the example that would use Pockels effect, a Chi2 nonlinearity, and which can be leveraged to do optical to optical conversion, also microwave to optical conversion. So you can write for in Chi2 picture, you can also write an electro-optical picture, the tensor. So this two tensor, you can see that they have the same symmetry. They're really determined by your crystal structures. For optical to optical conversion, the device I mentioned earlier, these device, we utilize this tensor element here, back to here. This tensor element, normally we call Chi33 here, this one. So this, in unredacted index will be ZZZ or 333. So that means you are looking at the coupling between the TM mode. And those are our device optimized for. So you are converting 1550 to 780 all TM mode. So the difference in the frequency conversion mode and the second harmonic generation are a little bit different, that the second harmonic generation only involves 2 modes. For frequency conversion, for optical to optical frequency, we actually operate in a non-degenerate mode. So one of the mode we treat as stiff pump. So they are both in a telecom regime. And when you treat this as stiff pump, then you can get a conversion from 1550 to 780 here. So as I mentioned earlier, you can quantify the cooperativity by looking at the mode splitting. And here we can measure directly the cooperativity as a function of this pump here. And if you send 80 milliwatt into the waveguide, you can get a cooperativity up to like 3.5. So to get a full conversion, you operate here at the cooperativity about 1. Here you get a peak of a bidirectional conversion here at the cooperativity equals 1. So if your 2 resonant mode are fully overloaded, that means the intrinsic loss does not play a role in your conversion system, you would have 100% conversion efficiency. Here in our 2 mode, these 2 modes, they're both undercoupled by about 3 to 4 dB, and that's why you got the total conversion efficiency about 14%. Okay, so these are the optical to optical conversion, and this is a similar device that inspire us to do microwave to optical conversion. And the device is a little bit different. It's the same learning as a ring resonator here, made of aluminum nitride here, polycrystalline aluminum nitride. And to support the microwave mode, we produce this ring resonator here, this microwave ring resonator here. And clearly the phase matching a little bit quite different. And in our geometry, we cannot use the previous like D33 element Chi2 tensor, because we like to have the microwave field in plane so we can have a stronger microwave field. So the nonlinear element that we're using this Chi2 tensor is R13 mode. So R13 means unreduct will be 113. and that means TM mode, right? So your microwave mode will be TE mode. So your two optic mode will be have the TE and the TM mode. So now the next step, you need to engineer your TE and the TM mode. Make sure they have phase matching with this microwave mode. So these turn out to be a big challenge because the optic mode has a much faster speed than the microwave mode. Sometimes it's vice versa, some microwave are faster. So the way we do that is to really to create an angular momentum in the microwave mode by building this ring resonator, have an angular momentum equals 1. Then we engineer this TE mode and TM mode, optic mode have azimuthal number differ by 1. In this way, you can get the phase matching. So you do spectroscopy with the optical mode here. And when the mode number, azimuthal mode number, they're very big, so around 1,000. So you basically, when they couple, you can see the transmission, you can see the mode splitting. Then when they couple, you have a mode splitting, and you can know that the TETM mode have exactly azimuthal number. However, the mode splitting normally on the order of 100 gigahertz. So we actually give us a little bit compromise of this coupling. So to reduce the TETM coupling, look at this TETM have azimuthal number a little bit of mismatch by 1 or 2. So in this case, we use 1. And here the mode splitting between TETM mode become around 8 to 10 gigahertz. And that fall into the microwave resonator frequency range. Now we can get the efficient microwave to optical conversion. So a lot of device engineering, both in the optical frequency and the microwave frequency, allow us to achieve this microwave to optical converter. And now if you think of this device, how to operate it is that you got a microwave connector, SMA cable, you got a fiber coming in to bring your local oscillator in, and you can print the microwave on the sideband of outgoing optical mode. And these conversion, again, is bidirectional, just I showed you earlier, like optical to optical conversion, and you can build this S matrix for microwave to optical, S11, S21, S12, and S22 measurement as a kind of a standard process. You can quantify what is your cooperativity. And what's most important that through this optical reflection measurement, you can see this tiny peak. That's the microwave resonance. You detect through optics. There's no microwave amplifier involved. So that's the microwave to optical conversion. In this specific device, we have a cooperativity about 0.075, and that translates this conversion efficiency from a waveguide to waveguide about 2%. Consider all the loss involved over here. Okay. So, so these devices are made of aluminum nitride without any moving part, and was made of a polycrystalline aluminum nitride. And recently we're making this our single crystal aluminum nitride. We also made a lithium niobate. And efficiency not necessarily getting better, but what we see that the noise get better. So they added, so this is a single crystal aluminum nitride. The structure a little bit more complicated, but it's the same principle. You lay down microwave circuit resonator and optical resonator and do the phase matching, and you can demonstrate the microwave to optic conversion. So the noise measurement turned out to be a really challenge for us because you shine the light on the superconductors, and that create a lot of thermal effect, and also you break the Cooper pairs that could generate the noises. We developed quite a few techniques to quantify the noise added by optical photon to the superconductors. So the way to do it, you could, so in collaboration with my colleague Michel Devry, what his group did, he attached superconducting transband qubits to our converter and then listen what is the added noise to that superconductor. And then they can quantify the noise, added noise to 0.03 quanta. And there's a lot of way to do it. We just use a temperature variable stage to support this microwave to optic converter. Then we vary the temperature from 40 millikelvin to 1 Kelvin. Then basically we create a black body source together with a conversion signal. And this black body source can be quantified with a very efficient readout circuits. This quantum limited traveled wave amplifier can read out the thermal photon with the calibration provided by the black body radiation. And we can also reach kind of a 0.03 imprecision of a measurement and a thermal occupation of a microwave mode. Here, horizontal axis is the optical drive. How much local oscillator, what is the intensity of local oscillator you add to the fridge, to the device. So you can see that your conversion efficiency is proportional to this optical drive. But your noise also go up from 0.1 noise photon to almost 1 noise photon when you have negative 24 dBm of pump power. Then when you go to negative 8 dBm pump power, your noise added by your converter is already twice bigger than one photon noise. So you get a 2 photon noise at negative 7 dBm. At this point, you really cannot drive it harder anymore because you're going to be overwhelmed. Your converter is overwhelmed by your thermal noise. So the trick we apply is to use a pulse drive. Okay, so the pulse on the order of like 2 microsecond pulse, and so that will not compromise your operation of your qubits, but reduces thermal node quite significantly. You can see that as you switch the pulse mode, your noise will drop by another 20 dB here. So if you can further increase your pump intensity, and at 0 dBm power, you start to have 1 noise photon. So those are very efficient technique to reduce the added noise to those converter. And we are improving this further. Hopefully, our next generation device, our thermal noise is going to stay at the 0.1 level at the base of the dilution refrigerator, base temperature of the dilution refrigerator. And that's something we're working on. Okay, eventually your system become really complex and you're building microwave circuits, you're building optical circuits in the dilution refrigerator. And so that's just a typical setup we use in our lab. And that's a refrigerator. That's picture takes 3 years ago. Right now it's way more complicated than that. And at this point, we just built this link from microwave photon to optic photon. We have not yet to directly connect this converter to the superconducting qubits. We use the qubits to measure noise, but we didn't use to deliver quantum information. So this bridge here is needed to be connected to really connect to the quantum computing nodes. Okay, so eventually we want 2 of those to connect together, and that will be another years of work. Hopefully, I convince you that this hybrid integration can be a powerful system for manipulating photon, both the detection photon and the generation photon, and convert the color photon coherently. And the work I show that really generation of a graduate student and postdoc contribute this work. Show the name over there. In the past 2 or 3 years, a lot of them suffer quite a lot. We are able to find some time, have fun, and do a lot of hiking. Well, I'd like to thank the funding agency over here and all the students working here. Thank you very much. Sure.
Yeah, so this is actually about the first third of your book. And you mentioned that you measure up to the
yes.
have 100 detectors.
Yes.
It seems like probably measure higher numbers, but it's just first half of that question. The second half, do you think that the G functions, the high order G functions, are better than pure probabilities for optical state characterization? So if you just did the analysis of probabilities P1, P2, P3, P4, as opposed to G1, 2, G3, G4, etc. Do you think one is better than the other, and so why?
I don't have an answer for you, but I can tell you what the limit of my G15 is the number of data I have to process. Too much data. Yeah, so maybe we'll have a more discussion about the P measurement, G measurement, opinion measurement. Right. Sorry.
You mentioned that you're able to use this R13 tensor coefficient, but you're using polycrystalline films. Does it require some order of the domains in the in-plane direction as well, or does it still give you an R13 even if the polycrystalline?
No. Actually, the polycrystalline, there is a one axis, a C axis always 3, right? So that's a line up. Thermodynamically, the only in plane is 1, 3, right? One and 2. So that is averaged out by 50%. So you don't compromise. It's not gone, but you compromise by 50%.
So it could be higher by 2.
Yes. Yes. If a single crystal, you higher by 2. Yes. Yeah, go ahead.
Question. So for your microwave resonator that you said has angular momentum 1, I'm just wondering if you could have made it differently. Like you had 2 inductive loops on that resonator.
Yeah, let me see if I can back up.
And I imagine, yeah. Yes. So, right in the upper left of that slide, I mean, we make some microwave resonators, and I'm just thinking, well, you know, you definitely want some electric fields there to couple between your optical waveguide and, you know, the currents traveling through that center loop. I'm just wondering how you think of it. It looks, yeah, it has interesting symmetry, and you know, you're also cutting the optical waveguide through one of the current leads. Can you describe the symmetry a little bit more from maybe the microwave standpoint, which is quasi-static?
Right, standing wave. Yeah,
it's standing wave.
It's a standing wave, right? So the point of that, so if you pull this electrode to this side, okay, just flatten it and put that electrode to that side. That's just a regular half lambda resonator, right?
Yeah.
The 2 end is a plus V, minus V, 0 in the middle, where you have a maximum current. So when you fold over, that was really nice. You keep the maximum electric field over here, which is allow you to apply this Park-House modulation. And that's the electric field going to that way, and that electric field also go that way, same way. So it's like your modulator, like a push and pull configuration. And that if you go around the circle, you actually see that your electric field change by pi. That's a very important. You go around the circle, your electric field changes by pi, that gives you angular momentum equals 1. If the electric field does not change the sign, then your angular momentum is 0.
Okay. Yeah, so you have those 2 strong electric field parts close to your optical waveguide.
Yes,
that's
yeah.
the main.
That's the main, right?
Design.
Right. Okay. Right. Ideally, you want to reduce make sure this inductor does not have any voltage drop over here. That you can optimize. Carter, yeah.
So I'm just wondering, you're trying to. So first of all, how close is the microwave resonator to your ring resonator, optical ring resonator?
About 5 micron.
About 5 micron. Okay, so then ideally your optical mode doesn't get affected by the presence of the conductor.
Yeah, so their wavelengths are different, right? Optical decay at half a micron wavelengths, but the microwave does not decay that fast.
Right. So then I was also wondering, like, if you've tried out any other optical cavity, shapes, just to other than ring resonators, to sort of reduce the mode volume and increase the overlap even more.
Yeah, that help. You can think of a photonic crystal cavity, but remember, in the end, there is a local oscillator mode. The photon number also help you to increase the efficiency, right? It's G0 times square root of m photon. So if you reduce your mode volume, your local oscillator photon can sustain in that the volume is reduced. So that there was a compromise. I think at Caltech, Oscar Painter's group doing excellent work with those smaller cavity devices. They have a very high efficiency and single photon coupling rate. It's very high. And that can reduce some of the overhead on filtering.
So my question was about the photon number resolving detectors. So did you mention like the detection efficiency? And I was also wondering like the design of the nanowire portions, like how you decide what to do there in terms of detection efficiency.
Yeah, let me go all the way to the back. Okay, so yes. So the detection efficiency. Unfortunately, this grating coupler, we like it, we hate it, and that was a problem. So once the photon get here, we get 100% close, but we don't even know we have 100%. We don't have a way to calibrate it. It's really lost from here. And so we have two calibrations. There's a Y spinnator, another Y spinnator. We make a square root. We know how much. We do the transmission from here to here, make a square root. We know how much going to the waveguide. That's the only thing we do. So the grating coupler efficiency is your limit.
Okay. But like in the diagram, you sort of show like the nanowire sections having like different lengths, like what is?
Oh yeah. Okay, good. You have very good observation here. So you see that you want each of the detector to take in 1% of photon, right? Absorb 1%. And of course, each detector is different. The detector at the native part of a waveguide has a disadvantage. So that's why we designed this to be a little bit longer. So this simulation can be well simulated how much absorption. That's deterministic. That's why it's a little bit longer. The last one is way longer than the first one.
How estimation you convert a microwave qubit into optical qubit for the fidelity of what you have an estimate of fidelity?
Right now, I can tell you our efficiency is very low. It's 0.1%.
Oh, it's not efficient, but fidelity.
Or how do you define the fidelity?
Like you have superposed microwave photon, microwave photon, and you convert into different polarization of optical photon, and what's the fidelity between them?
You want to verify the entanglement. That's what you're saying. Right now, with the thermal noise, we have that even 10% of a photon noise is a challenge. We have not in a position to evaluate that yet. And I think nobody has done that yet. Right now, a lot of microwave-to-optical converters, they're just readout. It's a readout. It's good cable. But that's already pretty good. They save a lot of cable. Okay, Tom.
You mentioned the optical effect and the electrostrictive effect, but aluminum nitride is also piezoelectric. Are you counting that as part of the electrostrictive effect? Or you?
Yeah, so that's the case. The clamped electro-optics and non-clamped electric. Right now, we treat ourselves as clamped electro-optics. So that's not coming into play at all. But if you have a suspended this aluminum nitride waveguide, then you have two things come together. The electro-optics and the piezo electro-optic, they all come together. Now you can engineer the device to either cancel them or enhance them. And it gets more complicated. They are on the same order. Right. So with aluminum nitride, it need to be easier to do it, to cancel it. And some of the material like lithium niobate is really complex, so highly anisotropic.
Any other questions for Hong?
Anything on Zoom? Good.
Okay, let's thank him again.
Thank you.